Hello everyone, today our group is going to present our topic, Application of Fourier transform in the communication system. Here is a quick overview of our presentation, and now let's hand over to my teammate.
So what exactly is a Fourier transform? In simple terms, it's a powerful mathematical tool that allows us to look at a signal from a completely different angle, shifting our perspective from the time domain to the frequency domain. The key takeaway I want you to remember today is this. Any complex waveform is simply to the sum of many different sine waves at various frequencies. Moving on to the definition. The core concept of the Fourier transform is converting a function of time, denoted as xt, into a function of frequency, xf. Here is a standard continuous time formula and it's on the picture. And I want to tell the pronunciation guide. X of f equals the integral of x of t times e to the power of negative j to pi ft dt. In this equation, xt represents our original time domain signal, while xf gives us the magnitude and phase for each frequency f. As you can see in the graphs here, the left side shows how the signal changes over time, and the right side shows its frequency components. Once we convert the signal to the frequency domain, it becomes much easier to identify the domain frequencies. Let's look at the intuition behind this. Imagine a really messy complex signal like the one on the top left. The Fourier transform showed us that this quality wave can actually be broken down into a series of perfect, simple sine waves. Each of these underlying sine waves has three unique properties: its own frequency, amplitude, and phase. A higher frequency means the wave vibrates faster. A larger amplitude tells us that this specific frequency is an important, dominant part of the overall signal, and the phase simply represents the starting position of that sine wave. So the transform takes a messy time signal and gives us a clear, organized breakdown of its frequency composition. Finally, why is the Fourier transform so incredibly useful to us as engineers? Because it makes solving many complex problems much simpler by analyzing them in the frequency domain rather than the time domain. For example, in filtering, we can easily remove unwanted noise and keep only the frequencies we want. In audio processing, we can see exactly which high and low pitches make up a sound. For images, it's usually heavily in data compression, noise reduction, and edge analysis. And in communications, it is essential for analyzing signal, bandwidth, and carrier waves. To summarize in one sentence, the Fourier transform is an essential tool for decomposing any time signal into its fundamental frequency components. Now that we have covered what the Fourier transform is and the math behind it, let's look at why communication engineers absolutely depend on it. If we only look at a signal in the time domain, what we see is voltage changing over time. That's fine for basic circuits, but it's a blind spot for communication systems. Why? Because the biggest bottleneck in communication isn't voltage, it's bandwidth. This brings us to a circuit mathematical property, time frequency scaling. The math tells us that if you compress a signal in the time domain, like transmitting digital pulses faster and faster, it expands in the frequency domain. In other words, faster transmission expands bandwidth. The Fourier transform allowed us to actually see and manage this invisible resource. But there is a bigger problem when we send signals into the real world. When a signal travels through the air or a wire, it doesn't survive perfectly. It bounces off buildings and gets delayed, creating multipath interference. Mathematically, the environment acts as an LTI system, and the distorted signal we receive is a complex convolution. Y of t equals x of t convolved with h of t. Calculating convolution in the time domain is near impossible here, but here is where the Fourier transform performs its greatest magic trick, the Fourier solution. It transforms that complex convolution into simple multiplication. Y of f equals x of f times h of f. If we want to recover the original signal, we simply divide. This elegant math is the exact foundation of the equalizers into your phone. So how do we use this multiplication to our advantage? Through filtering. In the mathematical idea, if we want to remove noise, we just multiply the signal by a filter function we design, like a perfect rectangular Brickwell filter. But there's a catch. If you take that perfect rectangle and use the inverse Fourier transform, it becomes an infinite sinc function in the time domain. This means a mathematically perfect filter is physically impossible to build. Therefore, we rely on the engineer compromise. We use real electronic components to approximate the math. The actual frequency response has a gradual slope and a specific cutoff frequency. It's a perfect bridge between pure mathematics and electronic design. Finally, there is the challenge of transmitting the signal over the air. Low-frequency signals require massive antennas. We have to move these signals to high frequencies. But how do we do that mathematically? The answer lies in the math. Frequency shifting property. The math proves that if we multiply our time domain signal by a high-frequency cosine wave, something beautiful happens. The equation shows XOF becomes 1/2 times the quantity, XOF minus F sub c, plus X of F plus F sub c. The result is efficient transmission via modulation. The original spectrum literally splits in half and shifts perfectly to the high carrier frequency Fc. This single mathematical property is what makes radio, TV, and calculator networks possible. And to show you exactly what this frequency shifting through lie in the real world, let's move on to part 3, the real-life applications. So far, we have seen what the Fourier transform is and how it's used to analyze signals. Now I'll show you where it actually lives. Real-life applications in communication systems. We will look at 3 themes: the classic example of radio broadcasting, how Fourier made the jump into the digital world through sampling and the FFT, and finally, the technology in your pocket right now, 5th generation and Wi-Fi. Let's start with something you have used your whole life, radio. Here's a question: why can't a radio station just transmit the sound directly? 2 reasons, and both come from thinking in the frequency domain. First, audio only occupies about 20 Hz to 20 kHz, so if every station transmitted there, all their signals would pile on top of each other. Second, the antenna would need to be kilometers long. The solution is modulation, which is really just the frequency shifting property of the Fourier transform. When you multiply a signal by a carrier wave, cosine of 2 pi fct, you shift its entire spectrum up to the carrier frequency. So AM station sits between 530 and 1700 kHz, FM station between 88 and 108 MHz, each one in its own slot. That's frequency division multiplexing. And when you tune your radio, you are literally picking one slice of the frequency spectrum to listen to. To use the frequency domain in a digital system, we first have to do 2 things. The first is sampling, turning a continuous analog signal into digital points without losing it. The rule is Nyquist-Shannon theorem, and is easiest to see in the frequency domain. Sampling creates copies of the signal spectrum based at the sampling rate, and if you sample too slowly, those copies overlap. That's aliasing, and the signal is ruined, so you sample at least twice the highest frequency. This is why the telephone carrying voice up to about 3.4 kHz, samplings at 8 kHz, and the music CD covering hearing about to 20 kHz, samples at 44.1 kHz. The second thing is actually computing the transform, and that's where the revolution happened. In 1965, Cooley and Turkey published the fast Fourier transform, cutting the cost of a discrete Fourier transform from the order n squared down to order n log n. And here's the part most people don't know. The FFT was first demonstrated to detect Soviet nuclear tests from seismic data during the Cold War, 100 times faster than the existing method, fast enough to keep up in real time. Today, IEEE lists it as a historical milestone, the algorithm behind almost every digital device we use. Which brings us to the technology in your pocket right now, 5th generation and Wi-Fi, both built on OFDM. Look at the transmitter. Your data stream comes in, gets split into parallel streams, and each one is mapped onto its own subcarrier. Then a single inverse FFT combines them all into one signal to transmit. The receiver simply does the reverse, using an FFT to pull the subcarriers back apart. Adding a cyclic prefix lets that FFT also handle channel equalization, which is exactly why OFDM became the core waveform of LTE, Wi-Fi, and 5th generation. To put numbers on it, 5th generation new radio uses up to 4096 point FFT with around 3300 active subcarriers, supporting bandwidths up to 400 MHz. Wi-Fi 7 goes further, 320 MHz channels and 4096 QAM, packing 12 bits into every subcarrier, reaching speed up to 46 gigabits per second. So here's the takeaway. Every Wi-Fi packet and every 5th generation frame you receive is a Fourier transform, computed billions of times a day all around you. For this part, I will talk about the advantages, limitations, and conclusion of Fourier transform. First, Fourier transform is useful because it can convert the signal from the time domain to the frequency domain. In the time domain, we can only see how the signal changes over time. But in the frequency domain, we can clearly see what frequency components are inside the signal. This is important in communication system because the engineers can use it to analyze signals, remove noise, and improve the quality of signal transmission. For example, if a signal contains unwanted noise, Fourier transform can help us identify the noise frequency and filter it out. Although Fourier transform is very useful, it also has some limitations. The main limitation is that it shows what frequencies are contained in a signal, but it doesn't clearly show when those frequencies appeared. In other words, after converting a signal into the frequency domain, some time information may be lost. This can be a problem when the signal changes very quickly, such as sudden noise or unstable signals. In this case, using only Fourier transform may not be accurate enough. Engineers may need to use more advanced methods, such as short-time Fourier transform or wavelet transform. Fourier transform plays an important role in modern communication systems. It is widely used in mobile phones, Wi-Fi, Bluetooth, and 5th generation. These technologies all need to transmit signals through different frequencies. By using Fourier transform, engineers can analyze frequency components, reduce interference, support signal compression, and make communication more efficient. For example, in 5th generation communication, signals are divided into different frequency components so that data can be transmitted faster and more effectively. So Fourier transform is not just a mathematical formula, it is actually a basic tool behind many communication technologies that we use every day. In conclusion, Fourier transform is an important tool in engineering mathematics. It helps us convert signals from the time domain to the frequency domain, which makes signal analysis much easier. In communication systems, it is used to analyze signals, reduce noise, support compression, and improve transmission quality. Even though it has some limitations, especially when dealing with rapidly changing signals, it is still one of the most important methods in signal processing and communication engineering. Therefore, Fourier transform is a good example of how engineering mathematics can be applied in real life, especially in modern technologies such as mobile phones, Wi-Fi, Bluetooth, and 5th generation.
Thanks for listening.